Great. Hello, everyone, also from my side. I will start today's series of talks with a short introduction into the topic of data anonymization, synthesization, re-identification, and risk analysis, but also utility analysis. And then Holger will continue and tell us more about the tools that have been developed as part of NFDI4Health. So let me start with a very, very general introduction, right? The idea of synthesizing data or anonymizing data in order to improve our ability to share it and reuse it for research purposes is usually that you take some personal data, usually individual level personal data, and you perform some form of process. It's called magic here. It can be very different things. There's a lot of approaches that have been suggested in various fields. And in the end, your result is protected data that ideally is also anonymous data in the legal sense, but that does not necessarily need to be the case. And that's exactly why we need further analysis to understand the data that we have produced. And this will be one of the major topics of the next couple of minutes. So if we dive a little bit deeper and see how this is done traditionally, then usually what has been performed on various occasions, but also studied a lot in the scientific literature, are, I call them, traditional anonymization methods here. And what does that mean? It means that you have an input data set that you want to protect, of course, and then you generate a protected output data set by applying transformations to the data, right? So by modifying the data. There's many different ways in which this can be done. And there's a few common examples shown on this slide here, which include taking a random sample, for example, of the data set, performing some forms of aggregation. Here we see that being done to the age variable, for example, maybe deleting certain values or complete attributes or complete records that lead to high re-identification risks. You could do masking or categorization or generalization, which are all three methods that basically are being used to reduce the fidelity of data, right? So we can see this here that weight, for example, is turned into a weight categories, or that a diagnosis is being generalized by removing the specific localization of the neoplasms that we are seeing here. And usually this process is done in a way that you try to optimize towards achieving certain goals, and those goals are usually goals in regards to how the data is protected from re-identification, but it can also be goals in regards to the utility of the data, so it can be optimized, for example, for certain applications. And for those of you who have sort of studied this field a bit before, you're probably aware of the well-known k-anonymity property, for example, which is one potential optimization goal, which basically says that you want to generate an output data set where records are indistinguishable from other records. In this case, the records are indistinguishable in the output data set from at least two other records. There's somebody in the call that is loud. Maybe you could mute yourself. That would be really good. Thank you. But what we also have here is the, how you say, fulfillment of a more modern privacy model, a version of differential privacy, which is a property of the transformation process itself, given under certain conditions. This can also be achieved, for example, in more traditional anonymization approaches, but it's also a method that is very well suited for being used in synthetic data generation processes. So if we contrast this with synthetic data generation, then synthetic data generation works quite differently, right? Here, the idea is that you have an input data set, you generate a model of that data set. It can be a model that is being created using statistical methods, but of course, modern methods of synthesization usually use some form of neural network that is being trained on the data, that learns important features and patterns in the data, and then you use this model or set of models to generate new data, right? So it's a fundamentally different approach, which has been shown in the literature to be able to produce synthetic versions of various types of data sets, not only including tabular data, which we will be looking at today mostly, but also, for example, imaging data, to a certain degree videos, right? So you all are also, of course, aware of this lots of tools in the generative AI space that exist nowadays, that are also able to generate various types of data. And there's different methods that can be used. We just recently, very recently, I think yesterday, published a review that we did of sort of methods that are used in the field. And what we found is that roughly 1/3 of the methods are generative adversarial networks, so a very popular technique for generating synthetic data. And then there's a wide range of different approaches in the other 2/3 of the methods that we found, which, for example, include Bayesian networks and also variational autoencoders, and also a range of, let's say, proprietary approaches that have been suggested or are provided as tools or services that you can use for generating synthetic data. And in NFDI4Health, to give you a sneak peek into the talk by Holger, there's also a tool that is particularly important, and that's the VAMP approach that has been developed by Holger and his team. And this combines, as far as I know, Bayesian networks with variational autoencoders. So even with synthetic data generation, I think that's an important point that I would like to make. There's a trade-off that you need to take when you try to protect data. And this is well known from the field of traditional anonymization methods, but also applies to synthetic data generation. And this means that let's say, at least in a very generic sense, if you want to study something based on a data set, of course, the most useful data set that you could have for this is the original data set, right? With all the potential quality problems that it might have, but also with all the fine-grained patterns and correlations and other statistical properties that are in the data. But that's not what you can have with data anonymization, be it being done with traditional methods or with synthesization approaches, but there's a new data set being generated or produced by modifying the data. And this means that there will be some form of loss of information and also some form of utility or usefulness of the data. And this needs to be balanced, right? And this can be drawn as a graph that we're seeing here on that slide, where you sort of trade off utility against protection. And ideally, you would, right? It would be great if here you could share the data just in its original form. This might be the case under certain circumstances, right? Also doing very little modifications to data or synthesizing a data set that is very close to the original data set does not necessarily mean that the privacy risk or re-identification risk is very high, because this is, of course, dependent on how high the risk was in the first place. So it also plays a role what data you have, how high risks would be for that data set. But the further you sort of deviate from the original data set, be it through modification, be it through data generation, the more you have the ability to, of course, reduce re-identification risks and introduce privacy protection, but you also potentially lose utility. And this means you need to somehow measure or consider utility in the first place, and you also need to measure and consider privacy risks. And both types of measurements are actually quite challenging to do. So just to maybe quickly comment on this, on the data protection or privacy protection side, this means that you somehow need to align what you can measure or introduce technically with what is required from the legal perspective. That's a complicated issue that we have also been working on a lot within NFDI4Health. And on the utility side, the issue is a bit that it's quite challenging to measure utility in a generic manner, but usually you need some information about what the data will be used for to make sure that the statistical properties or patterns that you use for that specific application are being preserved by the data, by the protected data that you produce. And in the synthesization space, for example, this can either be done by the model itself when it is being learned from the data, but there's also approaches where you can sort of give hints to the learning or model generation process on what specific properties are particularly relevant. And it's also an interesting question to study whether synthetic data actually provides better trade-off than other approaches, right? I mean, there's a few areas where obviously synthetic data generation is much better able to protect data sets than a traditional modification process would be able to do. This is for all high-dimensional data sets, images, time series data, where it's very challenging to modify data so that it becomes, for example, less unique. But for, let's say, smaller study data sets, it's not immediately obvious this data synthesization necessarily provides a better trade-off than traditional anonymization methods do. And this is also something that we have been studying in NFDI4Health based on a process that we use for re-identification risk analysis that I will show on the next slide. We also studied this in our literature review. How do publications that produce protected medical data or suggest methods for doing this measure re-identification risk, and also how do they study data utility? And what is quite interesting is that we found that there's actually a lot of methods that don't provide any provable guarantees, so there's no privacy protection mechanism baked into the method. But at the same time, they also do not perform a residual privacy risk analysis, right? So it's quite interesting. There's a large number of papers that they claim that they have a method developed for generating protected synthetic data, but there's actually no evidence within the paper that this actually protected data that is being produced. There's also a large number of papers that does not have a privacy protection method baked into the approach, but at least there is a residual privacy risk analysis being done that somewhat shows that there is a degree of protection. And what we can also see here, that there's quite some room for future research working on methods that are well able to synthesize data, but at the same time have sort of baked in provable privacy guarantees. And again, a sneak peek into the talk by Holger, which you will see here shortly. And there's a tool within NFDI4Health, Syndat, that can be used to do re-identification risk analysis, but also utility analysis. So the high-level re-identification risk assessment process that we developed within NFDI4Health is not only a technical method, so I won't go into a lot of detail here, for measuring various types of risk-associated metrics from the data, but also an approach that allows you to model the context in which data is being shared. Again, that's an interesting topic. Do I need to, or does it even make sense to assess a data set for residual privacy risks as a whole, or is it actually necessary to model the context within data in which data is being shared, and variables that might be, for example, known to adversaries, to actually generate meaningful results on the re-identification of privacy risks within a data set? There's also literature on this, and it's an ongoing, let's say, question and discussion within the community that works on these types of things, whether modeling the context is important. And in this process that we developed for NFDI4Health, we decided to model the context. So there's a component that allows you to model adversarial scenarios. And then in the end, out of those adversarial scenarios, there's a range of metrics that are being calculated. And those metrics, I'll show this on the next slide, are calculated in a way that they can be applied to traditional anonymization procedures or data that has been produced with traditional data anonymization procedures, but also to data that has been produced using synthesization methods. And this is just to give you a quick overview of the tool that we have been working on for modeling the context, that we will also use as a part of the service that we will provide the hopefully upcoming next funding phase of NFDI4Health. And here you can see basically that you can sort of categorize and rate the data set, and then get information on what data might be particularly prone to re-identification and needs to be considered when protecting a data set, but also, for example, when doing a residual risk analysis. And out of the measurement process that we then do, there's a range of indicators that come out. And as I mentioned, the interesting part here really is, and it's not something that has been studied a lot in the literature before, is that those metrics can be applied to synthetic data and anonymized data to perform some form of comparisons, and also gain insights into what I mentioned before, the question whether or not synthesization works better than traditional anonymization in a certain context. And this, as it's shown on the slide, can also be done by considering sort of the adversarial modeling of the context that has been done versus just sort of making a worst case assumption and taking a look at the complete data set when doing that analysis. And What we've also done, we've used this and related approaches in various studies, and I'm already in the process of wrapping up my quick introduction into the topic by providing you a few more concrete examples that we have been working on before we'll hear Holger's talks with the tools that are provided within NFDI for Health. Here's a recent study in which we did something that I find quite interesting. We compared how well synthesization works versus anonymization regarding utility and risks. Won't go into details on the numbers here. You can see that both of them somewhat work, but also have residual risks. But then we also performed a combination of both methods, right? So taking traditional anonymization procedures to generate a data set that has been protected as far as you can get with those traditional methods, and then use the anonymized data set to train a model and synthesize data. And this has actually been quite competitive in the study that we did, which is on calculating heart failure risk scores, and where the combination of both methods actually achieved a better privacy utility trade-off than any of the two methods alone. What we also did on focusing a lot on the utility assessment side, again, I find that quite interesting around the question, where are benefits and drawbacks of synthesization versus traditional anonymization, is that we reproduced a study on children's health in Slovenia. And really went through the exact original study and tried to see whether the original hypotheses still hold or don't hold, whether you would generate exactly the same insights using protected data versus using the original data set. And again, I won't go into a lot of details, but what you can see here is that so if you would exactly produce the insights of the study, you will only have green check marks here. And you can see that this is not the case for any of the methods that we studied. And there's, for example, anonymization procedures indicated by ARX here, but also synthesization procedures such as SynDiffX, which sort of, how do you say, work equally well in reproducing the study results. But there's further drawbacks and benefits. For example, very often for synthesization, there's not a lot of configuration that needs to be done. It can be quite an automated process, depends a bit on the method, while with traditional anonymization procedures, you really need to specify exactly what can be done to the data. So point I would like to make is, in addition to just being able to replicate results, for example, or fall below certain risks, there's of course additional access that can be considered around, for example, the sort of simply usability of an approach and how easy it is to use in practice without a lot of upfront effort. So last slide to conclude that, there's different benefits and also open questions around synthetic data and data anonymization. Synthetic data does have the benefit that potentially you can get very strong protection against re-identification out of that data, right? Because it is a process that involves some form of randomness. So there is no obvious direct link between the synthetic records that you generate and actual individuals. However, there's other privacy problems that can arise, inference attacks, membership attacks, and very often, as we've also seen in the review, there's no formal guarantees that are being provided by such approaches. And but you can synthesize quite complex data sets, also high-dimensional data sets that you could never protect in the same sense with traditional anonymization methods. And there's further aspects that need to be considered. For example, the fact that data is random and not truthful is, of course, a problem in science. And that's why Juliane Fluck, for example, mentioned in the beginning that a good process could be you hand out a synthetic data set to prepare your study, but your study is then in the end executed on real data. And with traditional anonymization, it's a bit different. There are other pros and cons, right? It is often possible to provide formal guarantees, but you do need some assumptions, which you might also need for synthetic data. It is more complex to configure. You cannot apply it usually to high-dimensional data. But what you very often get, at least with a lot of anonymization method, is truthful changes to the data and no sort of real noise that has been introduced. And yeah, final sort of conclusion, I would say there is an individual risk and utility analysis that is needed in either case, no matter how you protect your data set. And this will be exactly what Holger will now be talking about. Which I guess is the point, Holger, where I hand over to you.
Absolutely. Yeah, thank you very much, Fabian. So I think this is what you described, a really excellent introduction, in essence, to what I wanted to talk about now. Yeah, so I hope you can now
Yes, we see your screen. It's not in
see my
presentation mode,
slides and full
but
screen.
no, it's not in
Oh,
presentation mode.
better?
Yes.
Okay, perfect. Okay, yeah. So in essence, I will now move a bit over to the details about synthetic data generation and, of course, specifically talk about the work that we have been performing here in the context of NFDI4Health. But before actually moving into more details, let me step back and just say a few words again here about the motivation also for synthetic data generation, because in essence, there are several ones. So on one hand, there is what Fabian and also Juliane partially already described. So basically, the idea to use synthetic data, which in essence means to train a generative AI model on real data, in order to facilitate data sharing. Yeah? So basically by providing, for example, data scientists a kind of a sneak preview to the real data. And then, of course, they can actually start implementing their workflows and their analysis while waiting for the access to the real data. Yeah? But if you see it from a bit broader perspective, there are indeed also other motivations behind. Yeah? So for example, one further motivation is to also augment simply real data with additional data, which in some cases, so for example, for imaging has been shown also to improve AI models then subsequently. A very important further motivation is also clinical study design. So for example, synthetically generated data could be used as synthetic control arms, yeah? So, and then be shared across different studies. Yeah? Also, in this context, one could use synthetic data to simulate counterfactual scenarios. So what if, for example, at a given point in time, a patient had received a treatment that he did not in reality? So such things are in principle possible with these type of generative models. And this is very interesting, of course, from a clinical trial design perspective. And last but not least, I would also like to mention simply educational purposes. Yeah? So obviously for example, training data scientists, it is often a challenge so that we cannot provide, for example, students access to real patient level data for data privacy reasons. Yeah? So, but synthetic data might here help to give them at least an idea. So of course, at the end of the day, this is something that, of course, Fabian pointed out also a lot. Yeah, so there is a reassessment of re-identification risk of such synthetically generated data necessary. So the synthetic data is in essence a sample from a statistical distribution that has been learned from the real data, right? And of course, there's a further aspect, namely the quality assurance. Of course, there's the big question at the end of the day, how good or bad such synthetic data might be. So as also mentioned before by Fabian, so in practice, what we use here as a generative AI approach in NFDI4Health is a method which we call variation autoencoder modular Bayesian network. So this is a combination in essence of two different approaches. So it's a kind of hybrid approach between so-called variational autoencoders and Bayesian networks. And this approach allows for generative modeling of entire clinical studies, really in a longitudinal manner. And it is actually also a so-called white box model, because in essence, it allows you to understand also dependencies between variables or variable groups. So you can actually depict the model in form of a network, such as the one that is shown on the right-hand side. Furthermore, and this is actually based on quite well-known theory, under certain assumptions, you can use then such a generative model also to simulate counterfactual scenarios. So for example, in the past, we have used this to simulate what if patients had, for example, a different age at the inclusion into a clinical study, or what if they had received a certain treatment from which we know what the average effect size is. So the Wammen model can also be trained in a differential privacy respecting manner, and it is available on the NFDI GitLab. And it's also updated. So in the meantime, we have actually a second version, and we are working now on a third version of it. So this is in essence the backbone for generating synthetic data. But of course, as said, so a big question is at the end of the day, how good is such data? What can I now do with it? And this is not a question that is in fact very easy to answer. So because the results of such a generative modeling effort may differ immensely between one data set to the other, or how you train models. So this is not really a priori clear in essence that the synthetically generated data is at all useful. So in general, considerations that might apply here and that we try to implement here from our point of view are two major aspects. So on one hand, there's the idea that the distribution, statistical distribution of individual variables should somehow resemble, so between the synthetically generated data and the real data. So for example, look here on the top right. So here you see a violin plot of real data on the left-hand side, synthetic data on the right-hand side, and obviously there are certain differences here, so that are obvious. So which, of course, then, point you to the fact that indeed here, specifically here for variables in this very high range here, so you may generate something in the synthetic data that's actually not visible in the real data. So there may be actually artifacts. But of course, also other considerations like the correlation structure important to notice. And here, for example, the bottom shows here a plot here of correlation matrices of the real and synthetic data, which one may also want to compare. Or, of course, also a low-dimensional projections of the real and synthetic data, which allow you to see. So simply or give an idea about the geometry, so to say, of the space. So and how far there might be differences between the real and synthetic data. So in general, so there's a certain workflow therefore behind. So it's in essence generation of synthetic data, evaluation of synthetic data, and accordingly then if the results of the synthetic data generation process might be not satisfiable, so then it may actually mean from a data scientist perspective that the model has to be adjusted and may has to be retrained. So in order to facilitate this process, as also Fabian pointed out, so we have come up here with actually a platform, a software called Syndat. So Syndat in essence allows you to come up with a dashboard representation at the end of the day, so which depicts on one hand data quality assessments. And I will talk about the different aspects of this quality assessment in more detail afterwards. And on the other hand, also data privacy assessments, which I will also then talk about a bit later. And the third aspect is in essence also simply the visualization of the data. So basically lower dimension embeddings of the data and also algorithmically supported outlier detection in order to understand in how far certain data points that the synthetic data contains may be considered relative to the real data as statistical outliers and may therefore raise concerns. So from a modeling point of view. So let me dive a little bit more into depth of the data quality matrix so that we have implemented in Syndat. So these are actually comprising three different aspects. So on one hand, there is the question in how far we can differentiate between real and synthetic data in a multivariate manner. So basically, in this we call discrimination complexity. And then there's the question, how similar are the statistical distributions of the real and synthetic data on individual variable levels? So this we call distribution similarity. And the third aspect is the correlation structure. How well is this actually preserved between real and synthetic data? So regarding the first point, so what we do here is, in essence, we train a machine learning classifier, a random forest, to differentiate between real and synthetic data. And the idea is here that, in essence, the worse this performs, this classifier, so basically if this classifier is more or less at chance level, so then this, of course, indicates a better synthetic data quality. So therefore, we convert the performance metrics, the discrimination metric of the classifier, the area under ROC curve, into a matrix of quality of the discrimination, which is then at best scaled such as it's 1, and at lowest such as it's 0. In a similar manner, we look into the statistical distributions of individual variables. So basically, you may think about this as if you had here two, in the simplest case, normal distributions, right? So and there's the so-called Jensen-Shen divergence, a mathematical measure or metrics which you can apply in order to measure how close these two distributions are with respect to each other. And once again, you can convert this then into a metric that is at best case 1, so meaning there's a perfect match, and at worst case 0. And last but not least, we look into the similarity of the correlation structure. So basically what we do here is we look into the difference of the correlation matrices between real and synthetic data. And we look this relative to what the so-called Frobenius norm of the real data is. So basically the relative error we make with the synthetic data compared to the real data. So this is the idea. And once again, so then this error is scaled in a quality score, so that it's the best case 1, so meaning there's a perfect preservation, and at lowest 0, so meaning there's absolutely no preservation. Yeah? So regarding the privacy aspects, so we have here relied on a published framework for quantifying privacy risks in synthetic data, and we choose this one because it turned out to be also relatively straightforward to implement. So there was also quite good code available. So this has been here published relatively recently in 2022. In essence, combines here 3 different aspects of data privacy. So one is the so-called singling out risk. So what is the risk to identify a real patient based on certain synthetic attributes? Second, the so-called linkability risks. So can we connect real and synthetic data with the help of certain external identifier that an attacker might have information about? And third, the so-called inference risk. So can we derive sensitive information about a real patient from non-sensitive data? And yeah, so last aspect then is the visualization. So, and again here, so this shows here plots of what SynDat here provides you with. So here you can see here in blue, for example, a visualization of the real patients data points here for a particular data set, then, and in orange then of the synthetically generated patients, and on the right hand side simultaneously here then an outlier score is calculated. So basically the more red, the higher the flag that this particular synthetic data point might be somehow abnormal in whatever sense to the real data. So that means it could mean so that there is something that is an artifact compared to the real data. Yeah, so to conclude here, so we have here in NFDI implemented and come up with different novel generative AI approaches. Wammen is one that I mentioned particularly here, but there's also another one here, multi-node, which is a bit more complex for a synthesis of realistic longitudinal clinical and epidemiological study data. So we have Wammen 2.0 now out and released in 24 on the NFDI4Health GitLab. Currently, we are working on further improvements of this method, so in terms of the code. And we have Syndat as a downloadable and usable tool for comprehensive synthetic data quality and risk assessment. There are also several papers that we have on one hand published here on this workflow here as a whole, in addition, of course, to the methods behind, the generative AI methods behind here. And I would also like to mention that we have currently also a joint work with Fabian here and review, which looks from a more systematic, meaning scientific point of view on the trade-off between synthetic data fidelity, utility, and privacy. So what are for us here, so the next steps in the remaining months here of NFDI? So on one hand, there are certain smaller issues here so that we want to implement. So for example, in some sense, in some cases, it is there can be artifacts generated in synthetic data, such that, for example, age differences between subsequent visits are smaller than 0 or something like that. This is, of course, impossible in reality. So these are things that can be fixed in post-processing steps in order to improve the synthetic data quality. So these are, in essence, heuristics that we can implement as post-processing steps. And another thing that we are currently exploring internally is in how far we could further facilitate the use of the WAMN 2.0 workflow using, for example, large language models in order to facilitate, let's say, a semi-automated model construction. Okay, so that's everything from my side, and I'm, of course, happy to take any questions.